All right, so when we talk about work, when you calculate the work done by a force, you're doing exactly that. You're calculating not just work in general, but the work done by a specific force. So in that example there, where I'm pushing the desk across the floor, it doesn't make sense to just say, what's the work? Okay, you have to be more specific. You can say, how much work did Mr. Hecker do? You can say, how much force did friction do? You can say, how much work did gravity do? Okay? So for each force, you need to consider the work done by that force. Follow? Okay, and I'm worried that that did not get emphasized in the video. All right? Now, there are really 4 different possibilities. Okay? And 3 of the possibilities make this equation way easier. All right? So possibility number 1. So everybody point for me. In that example, which direction did the desk move? This way, right? So when I said, what are the forces on it, all of you said gravity first. Good, you should always start with gravity. Point for me, which way does gravity go? Down, right? So you'll notice in that example, the displacement's this way, gravity's this way. What's the angle between those two things? 90 degrees, right? What's the cosine of 90? 0, right? So one of the options is this. It turns out that if the force that you're considering is perpendicular to the displacement that your object goes through, then that means that your angle is 90 degrees. So the work done by that force is going to be, well, however much force you've got, times however far it moved, times cosine of 90 is 0. So you're just going to get 0, right? Does that make sense? Does it kind of make sense to you that as I push this desk, is gravity doing anything to the desk that would change its energy in any way? No, even if there was no gravity, if I pushed this, I mean, this scenario here isn't any different with or without gravity, right? I guess indirectly gravity accounts for friction, right? But gravity itself doesn't have any direct impact on how this desk moves when I push it. Make sense? So it's not doing any work. It's not changing the energy, okay? Now, second possibility. Point for me. Which way was I pushing it? This way, right? Which way is the displacement? This way, right? So displacement, force of Hecker. What's the angle between those two vectors? 0. So if your force is parallel to your displacement, then the angle between them is 0 degrees, right? So what's the cosine of 0, you guys? Cosine of 0 is not 0. Sine of 0 is 0. Cosine of 0 is 1. Right? Because it's like right along the x-axis. Okay? So I'm going to have force times displacement times 1. So if your force and your displacement are parallel, then your work is equal to force times displacement times 1. Good? Everybody good with that? All right. Option number 3. Point for me. Which way was the desk moving? This way. Which way is friction? This way. What's the angle between those two vectors? 180, right? What's the cosine of 180? -1, right? Because it's all the way over here on the negative x-axis, right? Am I facing the right way for this? Yes. Okay? So, I'm going to use some new notation. You may not have seen this before, depending on where you're at in math. So, do you guys agree that these two vectors are parallel and these two vectors are parallel? But we need a way to distinguish between them. Okay? So from now on, if they're parallel and they point in the same direction, I'll call that parallel. If they're parallel but they point in opposite directions, we will call that anti-parallel. Okay? So, notation. Parallel, they both point in the same direction. Anti-parallel, they point in opposite directions. Does that make sense? So if your force is anti-parallel to your displacement, in other words, if they point in opposite directions, then your angle is 180 degrees. What's wrong? So what's my work now? Force times displacement times, what's the cosine of 180, you guys? -1. So you just get negative force times displacement, right? Basically what that negative is doing is it's understanding that my force and my displacement are in opposite directions. So one of those two things has to be negative, right? So you're losing energy. The work done there is negative. So you've got negative some amount of force times some displacement. So this sort of puts the negative in there for you. Make sense? All right. So the moral of the story is the only time that I want to see you using this mess is if your angle isn't 0, 90, or 180. Does that make sense?
Yes.
Follow?
Yeah.
All right. So when we get to 6.5, oh, I need to talk about the other changes I've made. Sorry. When we get to 6.5, we will learn a little bit more about the significance of this work. Okay? At this point, here's all I want you guys to understand. Work in some fashion changes the energy of an object. It might change the GPE, it might change the EPE, it might change the KE, it might change the total energy. In some way, work always changes the energy. Cool? All right. Now, as you're doing the worksheet, or as you did the worksheet, one of the things that I think will make your life easier if you get stuck on these problems is make a three-body diagram. Okay? Particularly on problems 4 and 5. All right? Finally, problem number 1 it's got, I don't know, Roy, or probably Roy, somebody lifting a 35-kilogram box. Okay? And the very first question says, how much force is needed to lift that box? And a lot of people are getting tangled up on that. So here's the deal. Look, start by making a free body diagram. So here's my 35-kilogram box. Let me redraw this here for somebody's watching at home. So here's my 35-kilogram box. Gravity's pulling it down with 343 newtons, just 35 times 9.8. So in order to lift this box, what does the force of U have to be? I know. It's been a while, right? Okay, so to lift it, you actually need, sorta, technically to get it moving, you need a little more than 343, right?
Yeah.
But then, once you've got it moving, then you need exactly 343, right? But eventually you're going to want to stop it, right? So now you want your net force to be down, so you need your net force to be a little less than 343, right? So at the beginning you need more than 343, then exactly 343, then less than 343. What does it all average out to?
343.
343. So it is widely accepted for problems like this. If the problem is about you just lifting a thing, or whatever, pushing a thing up a ramp, that the force that you need is just the amount of force that you need to make your net force 0. Okay? Unless the problem implies some sort of obvious acceleration. Make sense? Questiones? Okay, so, that is that. All right, other stuff that you need to know. I didn't do a great job explaining the